Charlotte Louise from Fungi.com, and today I'm going to do a quick video about how to use the general fantastic physics equation. Now this is an equation that isn't ever going to be given to you in a test, but it's something really useful to use because you'll very often be given two-dimensional projectile equations where you have something being shot off or kicked off or thrown off some sort of cliff. And you'll probably either be given exactly how far it's going to go in the x direction and how far the cliff is in the y direction, and then be asked to find sort of the initial velocity and the launch angle. Or you might be given some other combination of the two, and you're going to need to find the third one. And if you start just plugging things in, you're going to end up with a really big mess on your paper. So this is just an easy way to sort of solve for one of these things given the other things. And so I'm going to keep everything in variable form, which is what I suggest you doing on a test or homework problem, because it's going to cause a lot less calculator errors. So basically the key to this problem is figuring out how long the projectile's in the air and just using the equations that we already have. So basically you're not really going to need the time at the top for this equation or for this problem unless you want to separate the problem into two parts. And you totally can do that. So you can use, if you feel more comfortable doing it, you can use the specific fantastic method that I have another video on to figure out exactly how long it's in the air to this point, to when it returns to its same level. And that would be twice t top for that amount of time. And then you know that when it leaves here, it's got this same velocity and angle that it started with, just in the opposite direction. So you know that this is true. And then you can sort of solve it in two chunks. So you could do part one up here, and then you could do part two, and this part two is just your standard sort of two-dimensional projectile, but you've got your initial velocity and angle already, and you know that the acceleration is still just the acceleration due to gravity. And so this is actually pretty easy to solve also. So you can do it that way, but that's still going to require two steps. So I would only do that if you really don't feel comfortable with what we're going over today. And that's an option, but yeah, I would avoid that one. Okay. So to start with how you would do this all in one step, we're basically going to use the equations that we have for dx, and then we also have our general equation for dy also. We're going to just use this one, equals diy times t plus 1/2 of the acceleration in the y direction times t squared. And the thing is, we have diy in terms of di and theta, and we also have dx, because we know that we don't have any acceleration in the x direction because this is a projectile, so the only force acting is gravity, which means that the only acceleration we have is the acceleration due to gravity. So we know our VIY, we know our AY, which is just gravity. We also know our VX in terms of that. So basically, to be able to get dy in terms of dx and vi, which is sort of what we're going, we want this all in one equation, all of these variables, we're going to need to get t in terms of dx and vi so that we can get it all in one. So that to do that, we're going to come down here and we're going to have dx equals vi times the cosine of the angle times time. And then we want to solve for time, so I'm going to bring that over. And we're going to do t equals dx divided by the initial velocity and what we know VIY to be equal to. So VIY is equal to the initial velocity times sine of the angle, and that's going to be multiplied by time, which we just solved for, and then we know this is shot up, so because I'm defining VI as positive, that means our acceleration is in the negative direction. So it's really important to keep track of your positive and negatives. So here we have negative half of 9.8 is 4.9. And then dx over di cosine theta, and all of that is going to be squared. So then we can just simplify, and we have basically everything we need right here. So dy equals sine over cosine, and that is di times dx. And then this one's just going to be minus 4.9 times dx squared over di squared cosine squared. And just like that, we have everything we need in one equation. So given that we have some of these in our problem statement, we can easily plug in and solve for whatever else we need. So that just makes it, basically all we had to do was realize what the time for this entire thing is going to be in terms of dx, and then plugging that into other equations we already know, we can get it all into one nice easy equation. So I definitely suggest knowing